Let's say we are given f of x is defined as the summation from n equals 0 to infinity of x plus 4 to the n over 3 to the n times n plus 1. And we're trying to figure out what are all the values of x that I could plug into this expression that would give me a series of numbers that would converge if I added them all together. Well, we know that the ratio test says the limit as n approaches infinity of the absolute value of the n plus 1 term over the a sub n term must be less than 1. So let's just say that we will start by letting x equal 0. Let's just see that if I plug in 0 for x, is that going to give me a series that diverges or converges? Well, with x is 0, we have the series 4 to the n over 3 to the n, n plus 1. Now let's just say that's our a sub n. And so now we want to write a n plus 1. And that's going to give us 4 to the n plus 1 over 3 to the n plus 1 times n plus 1, which is n plus 2. So now we're going to follow the ratio test, and we're going to divide them. So that's going to give us 4 to the n plus 1 over 3 to the n plus 1 times n plus 2. And we're going to multiply by the flip of a sub n, which is going to give us 3 to the n over 3 to the n times n plus 1 over 4 to the n. And we're now going to break this up as 4 to the n times 4 to the first. And then on the bottom, we're going to break that up as 3 to the n times 3 to the first. And then n plus 2. And on the top, we also have 3 to the n, n plus 1. And on the bottom, we still have 4 to the n. And now we're going to see what cancels. Well, our 3 to the n's cancel, and our 4 to the n's cancel, and we're left with 4/3. And we want to take the limit as n approaches infinity. We're going to bring the 4/3 out in front of the limit, and we're left with n plus 1 over n plus 2. Well, this limit is simply 1, and times the 4/3 in front, so we get 4/3, which is greater than 1, so this is going to diverge. Now, let's go ahead and try, let's say when x equals, let's say, -2. When x equals -2, you have -2 plus 4, which is 2. So a sub n, when x is -2, is going to be 2 to the n over 3 to the n, n plus 1. And so our a n plus 1 is going to be 2 to the n plus 1 over 3 to the n plus 1 times n plus 2. So we're going to divide, and we're going to get 2 to the n plus 1 over 3 to the n plus 1, n plus 2. And you may see where this is going. We're going to flip and multiply this one. We're going to get 3 to the n, n plus 1 over 2 to the n. And we're going to cancel some things out. So this 2 to the n is going to cancel with that 2 to the n, leaving us with 2 on the top. And then this 3 to the n is going to cancel with that 3 to the n, still leaving us with a 3 to the first on the bottom. And 3 and then an n plus 2. And we're going to take the limit as n approaches infinity. Well, this is going to simply be 2/3. 2/3 is less than 1, so therefore this is going to converge when x is equal to -2. But it diverges when x is equal to 0. So the question we want to explore in this video is, how can we figure out the range of values for x such that when we plug them into the function, we get a series that converges? Okay, we're given the series summation from n equals 1 to infinity of this expression. And so we want to use the ratio test. So we want to use the ratio test to determine the radius and the interval of convergence. Once again, we want to figure out what's the range of x's that I can plug into this series that would give me a series that converges. So we're going to write this out as the limit as n approaches infinity. This is the ratio test, the absolute value of a n plus 1 over a sub n, and that must be less than 1 in order for the series to converge. So let's go ahead and write that out. So our a sub n plus 1 is going to be negative 1, and you're going to plug in n plus 1 for n, which is going to give you an n plus 2. And then we have an x minus 5 to the n plus 1. And all of that is over n plus 1 times 2 to the n plus 1. Now we're going to multiply that by the flip of a sub n, which is the same thing as dividing by a sub n. And a sub n is our given function. So up here we're going to have n times 2 to the n. And on the bottom we're going to have negative 1 n plus 1 times x minus 5 to the n. Now we're going to rewrite all of this so that all the exponents are broken up. So over here we'll write this as negative 1 to the n, and then negative 1 squared, and then x minus 5 to the n power, and then x minus 5 to the first power, and then n, then 2 to the n. All of that's on our numerator. And on the bottom we will have n plus 1. And then we'll break this up as 2 to the n times 2 to the first. And then we'll break this negative 1 to the n plus 1 up as negative 1 to the n times negative 1 to the first. And then finally x minus 5 to the n. Now we're ready to cancel some things out. And let's see what we have. Well, an x minus 5 to the n is going to be canceled out. 2 to the n is going to cancel out. And negative 1 to the n is going to be canceled out. Negative 1 squared is just simply 1, so that's gone. And let's see if there's anything else that we can cancel out here. Nothing else. So therefore, we're going to continue to write our limit. So our limit is going to be the limit as n approaches infinity of the absolute value of x minus 5, in parentheses, times n over, on the bottom we have n plus 1, and then 2 to the first times negative 1 is negative 2. And we need for that to be less than 1. Now, notice our limit only depends on n. So we can factor out everything that is not an n. So I'm going to take outside of here the absolute value of x minus 5. And the absolute value of negative 2 is just 2. So I'm going to take that out. And now I'm going to multiply that times the limit as n approaches infinity. So once again, the limit is depending upon n. So we can take out things that are not an n. So that's going to give us a nice, easy limit to evaluate. So the limit as n approaches infinity of n over n, well, the powers are the same, 1 and 1, so that's just going to be 1. So we have the absolute value of x minus 5 over 2, and that must be less than 1. Now, we need to figure out how to deal with these absolute value bars. Well, if we go back to algebra, you will remember that, let's say you have x plus 3, absolute value is equal to 4. Well, you need to take the absolute values bars off by saying x plus 3 is equal to 4, or x plus 3 could equal negative 4. Let's see if they both work. Subtract 3 from both sides here, and you get x equals 1. Let's see if that works. Plug in 1 right there. 1 plus 3 is 4. Absolute value of 4 is 4. Over here, you subtract 3 and you get x equals negative 7. Negative 7 plus 3 is negative 4, but the absolute value of negative 4 is 4. So that's the reason why you'd have to always set it equal to the positive and the negative. So the same thing is true here. We're going to take our absolute value bars off, and we're simply going to put it between the values of 1 and negative 1. Now we're going to multiply by 2 to get rid of this 2. So that's going to give us negative 2 less than x minus 5 less than 2. And now we're going to add 5 to all three parts. And so running out of space here, so let me erase some stuff here. So if we add 5 to both sides here, we get 3 is less than x, which is less than 7. And that is what's called our interval of convergence. So our radius is 2 because this function, as you can see, is centered at 5. And so from 5, it's 2 to the right to get to 7 and 2 to the left to get to 3. So what does this mean? It means all x's between 3 and 7, if I plug them into this function, if I plug it into this expression, will give me a numerical series that will converge to some number. Now, here's the last thing that you need to do. You need to check the endpoints. You need to see whether it converges at 3 and at 7 or neither. So we need to plug those in. So we're going to plug 3 into our function. We're going to check and see if it converges. 3 minus 5 is negative 2. So let's see what we have. We have negative 1 n plus 1, negative 2 to the n over n times 2 to the n. And so now we are going to see if this converges by the ratio test. So let's just see what we have here. Well, tell you what, we can factor out a negative 1 to the n here. So that's going to leave us with, let's see if we can simplify this. This is going to be negative 1 to the n, and that's going to leave us with 2 to the n. All right. And so on the bottom, we have n and 2 to the n. So this is going to cancel out. And now we have like bases. So therefore, that's going to give us negative 1 to the 2n plus 1 over n. And so let's see if this one converges or diverges. Well, this looks like it's going to diverge, because this is going to be a harmonic p-series. This actually does not cause it to alternate right here, because this 2n plus 1 always gives you odd numbers. So that's always going to guarantee the top being a negative number. And so this is going to diverge because it's a p-series. And so we're not going to include 3 as a number that would make this converge. Now we're going to check the other endpoints. Let me create some more space, and let's erase this. Long problem, but hopefully you guys are getting the idea. Now we're going to see if this converges at 7. So 7 minus 5 is 2. So when we plug in 7, we get negative 1 to the n plus 1 times 2 to the n over n times 2 to the n. Well, conveniently, the 2 to the n's are going to cancel out, and we get negative 1, so summation from n equals 1 to infinity of negative 1 to the n plus 1 over n. We recognize this to be an alternating series, and so it's alternating series, check. The terms are decreasing, check. And the limit as n approaches infinity of 1 over n is 0. So this is going to converge by the alternating series test. So that means we need to have a line underneath this one. So it's basically going to be in interval notation 3 to 7 with a bracket. And this is called the interval of convergence. Okay, we have another series here, and we need to find the radius and the interval of convergence for this. So, once again, we're just going to jump right in, and we're going to write this with a to the n plus 1. So we're going to say this is going to be negative 1 to the n plus 1. And then we need to be careful here. This 2, we need to replace the n with n plus 1. And then there's another plus 1 right here. So that's going to be, after you distribute, it's going to be 2n plus 2 plus 1, which is 2n plus 3. So this is going to be x to the 2n plus 3 over, same situation here, 2n plus 3 factorial. Now that's our a sub n plus 1, and we're going to multiply that by the flip of our function, which is going to be 2n plus 1 factorial over negative 1 to the n times x to the 2n plus 1. Now we're going to try to break everything down. So that's going to give us negative 1 to the n times negative 1 to the first. And then we have x to the 2n, and then x to the third. And then we'll leave this alone for now. And then on the bottom, we will have, we're going to break this 2n plus 3 factorial down as 2n plus 3 times the number that came before it, which is 2n plus 2, times the number that came before that, 2n plus 1 factorial. And then we still have a negative 1 to the n, and then an x to the n. So we'll break this down into x to the 2n times x to the first. Now we're going to cancel some things out. So we have negative 1 to the n, negative 1 to the n, x to the 2n, x to the 2n, 2n factorial and 2n factorial are gone. X to the first, and one of these x's here is going to leave us with x squared on the top. So after everything is broken down, we have left a negative 1 to the first power. So I'll put that there. We have an x squared here. And then on the bottom, we have a 2n plus 3 and a 2n plus 2. Don't forget, we are trying to use the ratio test. So we're taking the limit as n approaches infinity of the absolute value of this thing, and it must be less than 1 in order for this to converge. So the negative 1 to the first, we're going to take that outside the limit. Well, the absolute value of negative 1 is just 1, so that goes away. The x squared is not, the limit is not dependent upon x, it's depending upon n. So we're going to take the x squared outside the limit, and that's going to leave us with x squared times the limit as n approaches infinity of 1 over 2n plus 3, 2n plus 2 absolute value, less than 1. So the limit as n approaches infinity is going to be 1 over infinity. That is 0. So essentially we're going to have x squared times 0 less than 1. And technically this should be an absolute value. So we're going to put this between 1 and negative 1. And so we have x squared times 0 less than 1. And this is less than negative 1. And the squared simply just goes away. And so now we are going to divide by 0, divide by 0. And any finite number divided by 0 is going to be infinity. So this is going to be negative infinity less than x less than infinity. So what does this tell us? This tells us that this series will converge for any value of x. The first example we did, it only converged for numbers between 3 and 7. Here it converges for any value of x. In this last example, we're going to do the ratio test again, and we are going to see the third example of how a series can converge or not converge. So we're going to write out our a sub n plus 1. So that's going to give us n plus 1. It's going to give us n plus 1 factorial, and then x minus 3 to the n plus 1 power. And we're going to divide that by our original function, which is n factorial x minus 3 to the n. And we want to take the limit as n approaches infinity, the absolute value, and this has to be less than 1. So let's break everything down. So n plus 1 factorial can be written as n plus 1 times the number that came before it factorial. And then we have x minus 3 to the n and x minus 3 to the first. And then we have n factorial and then x minus 3 to the n. And so let's see what cancels here. X minus 3 to the n is going to cancel with x minus 3 to the n. N factorial is going to cancel. And so that's going to leave us with the limit as n approaches infinity of n plus 1 on the top and x minus 3. Absolute value must be less than 1. So now the limit is dependent upon n, so I'm going to pull on the outside the absolute value of x minus 3 times the limit as n approaches infinity of n plus 1. Now as n approaches infinity, this limit goes to infinity. So what we have here is the absolute value of x minus 3 times infinity is less than 1. We take off the absolute value bars, so that's going to give us a two-sided limit. Don't forget times infinity. And we're going to divide by infinity, divide by infinity, divide by infinity. And so this is going to give us, well, 1 over infinity is just 0. So let's continue that down here. Less than x minus 3. And 1 over infinity, once again, is 0. So if we add 3 here, add 3 here, add 3 here, then what we get is 3 is less than x is less than 3, which basically is saying that this series only converges at its center, x equals 3. It only converges at one point, as opposed to the last example that converged at every single point, as compared to the first example, which only converged within a certain range of x's.